Hi, I'm Yash and I'm going to talk about our work Spatially Aware Multimodal Transformers for TextVQA. We study the TextVQA task which requires the VQA model to reason about the text present in an image to answer a question. For example, in the left image, to answer the question who is the author of the book at the top of the stack, the VQA model has to reason about three things. First, whether the question is about the text. Majority of the questions in the TextVQA dataset fall under this category. Second, it has to look at the relevant text amongst the other clutter. Third, it has to also decide whether the answer can be generated only by viewing the words that are detected in the text or does it need any additional vocabulary. To solve this task, recently M4C architecture was proposed. Let's walk through an example to understand how it works. We are given a question, what is the speed limit of this road? And this image and the OCR and the object tokens that are detected in it. We take some multimodal transformer layers and feed the tokenized question, object, and OCR embeddings to them. We generate the answer by stepwise decoding. We push in a start token and compute the similarity of the predicted embedding with the static vocabulary and the OCR embeddings. Finally, an argmax is taken to decode the steps output. We repeat this autoregressive decoding for n steps to decode the final answer, which could be a combination of OCR and vocabulary words. For our example here, we decode the 75 from OCR tokens and select the MPH from the static vocabulary to give the final answer 75 MPH. Let's analyze some failure modes of M4C. We notice that it tends to make similar types of mistakes while reasoning about the spatial relations in the image. These fall into two main categories. First, it fails to understand the relative spatial references. For example, in the left picture, when asked about the number on the right machine, it replies with the number on the left one. Second, it also fails to understand that text is written mostly from left to right or top to bottom. When asked about the book on top of the stack, in the middle image, the M4C correctly decodes the first word but degenerates later. To fix these issues, we propose a spatially aware transformer layer that explicitly consumes a spatial graph of object and OCR tokens and utilizes it to induce sparsity and provide spatial information during self-attention. Let's walk through an example to understand how our spatially aware transformer works. In this, we have an image with two players and a bunch of OCR tokens and objects detected. We build a spatial graph of the OCR tokens and objects by connecting their centroids. We categorize the relationships between two nodes in 12 different categories, where 8 of them come from the angular distance between the two nodes, with x-axis as reference, and 3 categories come from overlapping object boxes. We also have a 12th self category. After categorizing the relations for each node in the graph, we build a sparse source-target attention matrix using it. Each head in our self-attention layer attends to a single type of relations, and this prevents the heads from learning redundant features across them. To induce the sparsity, we add a bias to the attention weights before the softmax layer. Now let's talk about the overall architecture. As with M4C, we start with visual, question, and decoding features as input to our new model. In our model, SM4C, we use 2 vanilla transformer layers at the base and 4 spatially aware layers at the top. Each spatially aware self-attention layer has 12 heads, with each head attending to a different relation category. We use a decoder network similar to M4C to decode the final answer. We choose TextVQA as our primary testbed. We start off by improving the baseline established by M4C. We add 2 new transformer layers, switch to Google OCR, and use beam search to achieve 2% gains. Adding spatially aware self-attention layers lead to additional 2.2% gain on test set. Overall, we push the state-of-the-art performance on TextVQA by 4.2%. Another dataset for the TextVQA task is SceneTextVQA. With our best model, we show 4.2% absolute improvement on ANLS metric on the test set. We ablate our model and also compare our work to other baselines from the NLP and VQA literature. Specifically, we compare against the following 3 models. A model with randomly initialized spatial graph. Second, a model which considers top 60 strongest connections during self-attention. And third, a model that uses additional bias embedding to encode spatial relation. We find that M4C outperforms each of these baselines. Next, we compare and analyze our model by reversing the spatial words in the question. For first example, we change the spatial word stop right from the question to bottom left and find that our model changes its answer accordingly. We also see similar behavior in the second example. Changing the word stop left to bottom right correctly changes the prediction of SAM4C, but not M4C. In conclusion, we introduce a new spatially aware transformer layer that prevents attention from diluting across object and OCR tokens and does not let the attention heads learn redundant features. For more details, please check our workshop submission. Thank you.